Okay, let's start. Welcome everyone at the last parallel session at this great conference. And we'll start with a talk by Naoki Sasakura from Kyoto University, Tensor eigenvalue distributions through field theoretical methods. So the floor is yours for the next 15 minutes, including discussion.
So thank you very much for the introduction. And, first of all, I'd like to thank the organizers for this very nice opportunity. And today, I'd like to talk about tensor eigenvalue distributions by using field theoretical methods. And yeah, this work is based on these papers. Okay. Not working. Okay, thank you. Yeah. And let me start with an introduction. And as you may know, eigenvalue distributions of matrix models play important roles in understanding atoms, two-dimensional quantum gravity, QCD, etc. And the most famous work in this subject would be the semicircle law by Wigner. And the natural question would be what roles eigenvalue vector distributions can take in tensor models. And actually, tensor eigenvalue vector distributions were previously studied in these papers. In these two papers, the expectation numbers of real tensor eigenvalues were computed. And in this paper, the estimation of the largest eigenvalue in the large n limit was given. And also in this paper, an extension of Wigner semicircle law was proposed. And actually, the real tensor eigenvalue distribution is the same problem as to count the critical points of the Hamiltonian, which is often called complexity of the spherical p-spin model for spin glasses. Actually, this has comprehensively been solved by a matrix model techniques in this paper. It's about 10 years ago already. And so therefore, the end results of this talk are not actually new. But however, the method we use is different, namely field theoretical method. So therefore, we can expect the method will give some insights and extensions different from the previous studies. And this will be mentioned briefly at the summary. And so let me start with what are the tensor eigenvalues and vectors. So in this talk, I restrict myself to consider only real symmetric order 3 tensor, CABC, and this large n denotes the range of the indices. And then the tensor eigenvalue vectors of tensor C is defined by this equation. Here, theta is the eigenvalue, and V is the eigenvector. And there exist some differences from the matrix case. For example, the eigenvalue problem is, in the matrix case, this problem is a linear equation, but here in this tensor case, a system of n nonlinear equations. And also, as you can see easily, this equation is scale invariant. So therefore, the definition here is not unique, and you have to properly gauge fix this ambiguity. And also, in the matrix case, a symmetric real matrix has only real and real eigenvectors, but in this tensor case, they are not necessarily real. Therefore, because of these differences and complications, there are some different notions of eigenvalues and vectors. The relevant notion in this talk is what is called Z eigenvalue. In this case, the eigenvector and the eigenvalues are all both real, and this ambiguity is fixed by normalizing the eigenvector. And in this talk, the purpose of this talk is to compute the distributions of real eigenvectors and eigenvalues. So the setup is that C is, as I said, symmetric real tensor of order 3, and it is assumed to be has Gaussian distribution. First, I consider this equation, which is real eigenvector, which determines the eigenvector distribution when the C is distributed by Gaussian. And here the eigenvalue is fixed to be 1. And then one can transform this the information of the distribution to the information of the real eigenvalue distribution. Here the eigenvector is normalized, and then the eigenvalue is given by the inverse of the size of the vector v. And as I said, what is new in this talk is not the end results, but the fact that we use field theoretical method instead of matrix model. Now let me define what is eigenvector distributions. So let me consider a certain C. Then the distribution of the eigenvector distribution is given by just by the summation of the delta functions located at the solution of the eigenvector. Because the eigenvectors satisfy this equation, so therefore this summation is nothing but just the delta function of the equation itself. But because of the difference of the measure, you have to correct this measure difference by introducing the Jacobian here. And then, so this is a case of one particular C. And when C is distributed by Gaussian, then you have to take the expectation value of this quantity. This is nothing but the integration over C with this Gaussian factor. So what the purpose of this talk is just compute this integration. Then you obtain the distribution of the eigenvector. And so to do that, I rewrite this integration in terms of field theory. And the first challenge is to rewrite this determinant factor, and then rewrite this delta function part. So now let me first rewrite this determinant factor. The challenge here is that you have absolute value. It's not analytical function, so therefore you have to do something to overcome this non-analyticity. So of course the simplest solution is just forget this absolute value. But still the problem is interesting. And in this case, this is just now this is just the determinant. So therefore, by introducing a couple of fermions, you can rewrite this determinant factor with this form. But of course, what we are interested in the distribution itself. So therefore, we have to do a little bit more. So one can try this expression here. Here, I have introduced two parameters, epsilon and r. When r goes to 1/2 and epsilon goes to 0, then this is expected to become determinant of this absolute value. And for integer r, one can rewrite this one by using a number of fermions again. So in this process of taking 1/2, you have to do an analytic continuation, but otherwise you can compute this quantity by this fermionic integration. But there is more direct way, and you can just rewrite this determinant factor by using fermions and bosons like that. Now another factor in this integration is the data function part. But this is very trivial because we know that this is just given by this integration expression. So therefore, what we generally have to do is this integration. Here, C is this first term is just expressing that the C is distributed by Gaussian, and this is the data coming from. This comes from the delta function, And this is the this is field theoretical. This field theoretical part is to deal with determinant factor. Anyway, this action has this quadratic and linear form in terms of C and lambda. So therefore, C and lambda can be integrated out easily. Finally, you obtain an effective field theory of bosons and fermions with quartic interactions. Oh, too mean? Really? Okay. So now what we have to do is to compute the effective field theories. For the case of forgetting the absolute value, what you obtain is this 4 Fermi interactions, interacting theory, and you can exactly compute the expression, and you obtain confluent hypergeometric function of the second kind, and you can compare the result with Monte Carlo simulation, and good agreement is obtained. And for the case of, real distribution, the action becomes quite complicated. But still, one can do that exact analytic expression for small nr in terms of error functions. And this is an example. And also, in the large n limit, you can use the technique of Shugin-Dasher equation. And it turns out that the eigenvalue distribution for large n limit is given by Gaussian in this form. And the result is compared with Monte Carlo simulations, and we obtain good agreement. So this is a summary, and so we have computed real eigenvalue vector distributions for order 3 real symmetric tensors with Gaussian distributions. I have obtained some exact analytical expressions, and the large n limit is shown to be Gaussian, which contrasts with Wigner's semicircle law in the matrix model. There are similar procedure can be applied for a little bit more general cases, and for example, correlations among eigenvectors would be very interesting, because we know that in the matrix models, eigenvalues are repulsive, and how about tensor model is a natural question. And also, we obtain exact analytical expression, at least for small n and r, but probably this is all true for any n and r. I want to understand this integrability. And there are some extensions of introducing allowance and backgrounds and complex cases and tensor rank decomposition. Okay, thank you.
Great, thank you very much for the talk that you fit exactly into this 12 minutes. And now we have a few minutes time for questions from the audience. Yes, please.
Just a question about, so once you know this eigenvalue for these tensors, how much do you know about the tensor? Can you, in the matrix, you can reconstruct the matrix from the knowledge of the eigenvalue? So what's the correspondence there?
I see. That's a very good question. And so it's eigenvector. I think eigenvector represents some, properties of the eigenvector, the tensor itself. But I think that the more direct relation can be obtained by tensor rank decomposition. It's kind of expressing the tensor in terms of a number of vectors, and this is correspond to the the singular value decomposition of the matrix. And so therefore, this represent more the the property of the tensor, but rather, currently I'm not so sure whether this, the eigenvector, how much eigenvector describe the tensor itself. Yeah.
Thank you. Is there are there any more questions? Then maybe I will have one more.
Okay.
I'm a numerical guy. I like to make simulations, and my question is: do you know if there are numerical methods to compute eigenvalues of some tensor? If there are any methods, or are they efficient, or what is the complexity? Or you don't care about numerical
You mean that
waves?
how I did the Monte Carlo simulation for this?
No, is there a way to compute that?
Yeah.
To diagonalize?
Yeah, diagonalize.
Diagonalization.
Or maybe some.
Again, I think diagonalization of the tensor correspond to this tensor rank decomposition rather than the eigenvalue equation, vector equation. Yeah.
Thank you very much, and let's switch to the next